Hello and welcome back. So right now we are in the process of setting up the FEM solution. So we have already looked at the first step, that is representing the solution in piecewise continuous format. So now let's look at step 2, formulating the equations within one element using the variational statement. So let's define the residual, which is really important. Any differential equation you could simply rearrange by bringing all the terms to the LHS, and the RHS would be 0. So write down this kind of format, f of u is equal to 0. So here f of u is the residual. So the idea is that if you plug in the analytical solution into f of u, the value goes identically to 0 all over the domain. But if you were to plug in a numerical solution or a guess solution, this would have non-zero values. Okay, and these non-zero values are a deviation which you could think of as an error. So now let's remember that finite elements comes primarily from a solid mechanics background. That is where it has a very strong foothold. And in solid mechanics, variational statements are common and they are directly tied to potential energy minimization. Okay, but we are interested in finite elements for CFD, transport, multiphysics sort of problems. So here writing a variational statement does not always relate itself to energy minimization. So we rather have to use this variational statement intuition and use an analogy and carry it forward to our multiphysics problems. Okay, so here I'm not going to write down a variational statement. Okay, so I am just going to show a thought experiment and let's use the analogy. Okay, so here we are using a thought experiment which is strictly looking at equilibrium cases. Okay, so let's consider this equilibrium case in which there is this thread which is hanging over these two nails and it is tied to this weight. Okay, so at the weight as the weight acts in the downward direction, you get a strong tension in this thread. So due to this, the profile of this highlighted part of the green highlighted part of this thread can be thought of as a flat line, right? Let's say I perturb this line, okay, and I allow it again to go back to steady state or equilibrium state. So you could imagine very intuitively that this would again go back to a flat line. Okay, so if this perturbation is really small, the system is not really changing. And in the first case, we already saw that when the potential energy of the system is minimized, you have this flat line. Okay, so after this perturbation is released, you would again go back to a state where the potential energy is minimized. Okay, so again a flat line. Okay, so now let's use this analogy. So now here I am making a statement which is not so accurate. So this is a very subjective statement. Don't look at it from a very objective physics point of view. This is just for developing the analogy or the intuition. Okay, so just as the perfectly taut string under uniform tension relaxed into a flat line, so imagine a situation where the residual of the differential equation flatlines under the effect of the analytical solution. Okay, so this is an analogy which we are using for connecting these two problems. Okay, one is a solid mechanics problem and one is a diffusion problem. So now let's think of a perturbation as well. So here you could think of perturbations as continuous differentiable functions inside the discretizations. So if I try to perturb this residual by just multiplying by this function and integrating it, I would still get 0 values, right? Because the residual is identically 0. But now if the residual was not 0, if I was using a numerical solution or a guess solution, now if I try to perturb it using these functions and integrate it, so I would get non-zero values. Okay, so now I can define an objective. So I could say that since u is an approximation, we know that it's an interpolated approximation. So I can say approximate u such that the integral of the weighted residual approaches 0 over the domain. Okay, so here g is being called as the weight. Okay, and this is the residual. So we can reduce our objective of forming the equations to this kind of an objective. Okay, so let's look at our diffusion case. It will become more clear. So since u2 and u3 are the unknowns which are basically defining this entire problem, so we can simply change our objective to finding the values of these unknown coefficients. Okay, such that again the integral of the weighted residual approaches 0. So now let's try to be more specific. Let's try to write down equations. So I'm interested in finding out the integral inside this element. So I have two unknowns, so I need to have two equations. Okay, so I would just multiply by two weights, g1 and g2. Okay, so that's pretty obvious. So now in finite element language, these functions phi, which we have used for interpolations, they are called as trial functions, and the g, which we called as the weights, so they are also called as the test functions because they are actually testing this interpolated approximation. Okay. So when you look at finite element blocks or finite element literature, so you might find the same kind of symbol being used for the test and trial functions, and this sometimes creates a lot of confusion. Now this is because the most commonly used FEM formulation is the Galerkin's method, and in the Galerkin's method the trial and test functions are the same. Okay, so you use the same symbol. Okay, but let's not get confused, they are different, they are totally different, they have totally different reason for being in the formulation. So in this lecture we are going to, or rather in this entire course, so we are mainly going to look at the Galerkin's method. So now let's try to define G1 and G2. So we'll put them same as phi2 and phi3. Okay, so now we have these two equations. Now can we solve them? So clearly these are linears, so second order derivative of that would be 0. Okay, but even if these were quadratics, I would not be able to solve them. So let's look at the reason. So the reason is that Lagrange polynomials, whether they are linear, cubic, quartic, quadratic, they are all C0 polynomials. Okay, so this means that they have this means that the 0th order derivative is continuous. Okay, the first order derivative is discontinuous. So let's look at this geometrically. So if these are my Lagrange interpolation polynomials, so this line has a constant slope, right? This solid line has a constant slope, which is shown by this dotted line, and at node 2 suddenly the slope changes to negative. Okay, so these are the slopes, right, and they are discontinuous. So even if I look at a quadratic representation, I can see the same thing. Okay, so the polynomials are continuous but their derivatives aren't. Okay, so what happens if the derivative is discontinuous? If I try to take a second derivative here, so I am trying to take a derivative of a discontinuity, so this leads to an infinite pulse, direct delta, and if I try to integrate this, this will just create blow-ups. Okay, here, so this is not possible. So so the first thing which would come to my mind is just use C1 continuity, right? So instead of using a sharp change in the slope, I could just smoothen this out. Okay, so this becomes C1 continuous. But the problem is that when we are dealing with real physical problems which have complex geometries in 2D and 3D, we still don't have a mesh generator which can create meshes which can be modeled by C1 polynomials. We can think of this in simple geometries and in 1D cases, but we cannot think of this in 2D and 3D. So what is the solution? One way to think of this is change of variables. Represent a second order problem as second order differential problem as two first order differentials. That's one way. But the more commonly used way is which we also use in the Galerkin's FEM, and that is the weak form. So here weak stands for the weakened continuity. Okay, so this weakened continuity really allows us to solve the partial differential equation. So now we are going into terrain which is entirely Galerkin's. So let's define this first, that we are using the same variable psi for the trial and test functions, but these are both different, and so I'll try to represent them using different colors, so this will be more clear. So now let's look at what is the weak form of the differential equation. So this is derived by using the integration by parts formula. So you might have already learned this in your undergraduate course, basic calculus course. So I'm not going to show this here. Let's just consider a du by dx, a differential equation which is defined in a 1D geometry between A, which is going from A to B, and now I have this test function. So now let me apply integration by parts. So this would break down into two terms. So the second term is basically the definite integral which is evaluated. So this is the definite integral evaluated at A and B. So these are the boundary, these are only present at the boundaries, right? And this term is really interesting because you can see that the derivative of u has transferred to the test function. Okay, so if we do this for a second order derivative, you can see that one of the derivatives that has transferred to the test function. So this has become a first order problem. Okay, all of the derivatives are first order. So now I can solve this. Now I don't have the problem of those direct delta functions. So let's look at this more clearly. Now let's actually show this domain geometrically. This domain omega, sigma are the boundaries, right? This is the equation, differential equation. So this is called as the strong form of the differential equation. Now I write the weak form by multiplying by a test function and integrating. I use integration by parts. I get I get these two parts. So this part is defined on the domain, okay, and this part is defined at the boundary, okay. So now I have shown the boundary, so I have also shown this unit normal dotted, unit normal in the outward direction, because this is the flux, right? Okay, so now let's move one step ahead. Now we want to write equations for one element, okay, one discretization. Let's assume just linear polynomials. So now these are only first order derivatives, so we can use linear polynomials. They are weighted by coefficients here, which I have not shown here, but we already know that. So these coefficients are u1 and u2. I have called them u1 and u2. So I have shown the trial functions in yellow and the test functions in white. Okay, so now one way of thinking about the weak form is that you apply the weak form on the discretization, and then the boundary terms, they have this unit normal in the outward direction, so they just cancel out in the opposite directions. Okay, from either side they just cancel out. So you don't have this term inside the element, so only you have this red term. Another way of thinking about this is apply the weak form globally, and so this term is only evaluated at the boundary. So in any case, you have only the red term being solved here. So we just have to use this red term for writing equation for the element. And so let's expand this. Let's expand u. So we know that u is this interpolation, and since these psi is really changing if with x, okay, so we can write it like this. So just expand this and you could write these kind of expressions. Let's do this for a source term. What would happen if this equation also has a source term? So we would multiply by a test function, again integrate, but we don't take integration by parts here, so no contribution to the boundary term. Okay, again let's write this out. Okay, so here the purple ones are the trial functions, the peach ones are the test functions. Okay, and now I have written this in a matrix form. Okay, so this is a local matrix. Okay, but here you have a variation with x. Okay, so let's remember that we do the mapping to the master element. We have already described this. So this is pretty simple. I can write x. So we already know this. X can be interpolated as well, right? So x1 and x2 are knowns here. So I can write an equation between x and psi. So we are using the master element psi going from 0 to 1. Okay, so to evaluate d psi 1 by dx and d psi 2 by dx, we can just use the chain rule. Very simple, basic calculus. So how do we evaluate this term, this yellow term? Just use this relation and take the derivative. Okay, how do we evaluate d psi 1 by d psi and d psi 2 by d psi? So these are simply the derivatives of this, which are constants, right? So we have already talked about this. They are -1 and 1, right? Slopes. So we can evaluate d psi 1 by d psi and d psi 2 by d psi by -1 by h and 1 by h. Okay, so plugging it into this equation for du by dx, you can see that this just goes to the finite difference kind of equation. But when you use quadratic interpolants, it won't be so simple, so you will find a complicated expression, but basically the idea is the same. Okay, you use the same kind of method. Okay, so now that we know d psi 1 by d psi, d psi 2 by d psi, we can write down the actual matrix. Okay, I'm sorry. So we have this j term here, which is the metric factor, right? So now we are in a position where we can actually start writing down this equation, but we don't know how to do this integral. Okay, so that is still missing. So we need to learn that, and then we'll be able to write the local matrix and then assemble the global matrix. Okay, so that we'll do in the next lecture. So thanks for paying attention, and I'll meet you again in the next one.